Okay, so this tutorial video is going to be a bit different than the others in that instead of giving you a procedure that you can follow step by step, I am instead going to give you some tips and tricks, some ideas, and hopefully by the end of the video you'll have some insight on how you can use the Tycho software to discover new asteroids. So this is pretty exciting because that's the primary motivation I had in developing the software in the first place. And yeah, I think synthetic tracking, which is the technique that we're using here, is pretty cool. The way it works, and I won't be going into detail in this video on synthetic tracking itself. I have other material that covers that, but the way this tutorial is structured is that I'm first going to show you the results, and from there hopefully that'll catch your interest, and then the other part will show you in more detail how I achieve those results, and hopefully you can then choose for yourself, you can decide for yourself whether or not you want to use synthetic tracking for your own project. So with that out of the way, let's go ahead and take a look at the results here. Okay, so with this example, I have a set of images here. These were acquired on September 1st of this year, so about 26 days from the time of this recording. And there are 60 images. Each exposure is 3 minutes in duration. So it's 3 hours total imaging time. So that's quite a lot, obviously, but it really, in this example, that just drives the point home that the longer you dwell on a field, the more signal to noise ratio you can achieve, and consequently the fainter object you can detect. So that's kind of the whole idea with synthetic tracking, is that kind of like the Hubble Deep Field image, they were able to detect thousands and thousands of galaxies simply by staring at a piece of the sky for several weeks at a time. So that's kind of what you're doing here. Now obviously there's a limit to this because the objects are moving, so a really fast moving object, you can't dwell on it for hours on end, it'll leave the field of view. But this gives you some indication of what you can do to start off with, and then with that you can then take that and say, okay, maybe I want to adjust some of the parameters, and maybe I want to detect faster moving objects so I don't dwell quite as long, or that sort of thing. So so what we have here, these are the tracks that have been generated. So I ran the synthetic tracker and it came back with these results. So the first thing you want to do is ideally you want to go ahead and see if you can match these up with already known objects. So you go to File, Load MPC Orb. What that is, that's the MPC Orbital database. And when we do that, it then matches each track and with a known object, if possible. So as you can see, a lot of these tracks, they're already known objects, and that's to be expected. But every now and then you see one that might be a candidate, a potential new discovery. So here's one example right here, and this is nice because it certainly looks like a valid object in this window here, and it's also moving at 1.3 arc seconds per minute. So that places it a little bit outside the bounds of a typical main belt asteroid, so meaning it could be potentially interesting. So the first thing you want to do is say, okay, is this potentially a new object? So we want to take measurements of it, so we load up the star catalog, and then we right click on the track and say verify. So it's going to give us an animation here, and we're going to say, okay, does it look like a true object? So we have a bit of star interference here. We can switch to a different view though, and when we do that, we see that indeed it survives the stack. So it comes out as a nice object that forms up, and I would say for sure that's a real legitimate object. So we go ahead and say, okay, add observations, and we don't have any designation, we just give it our own track identifier, and click OK. So when we do that, it comes back with 3 measurements, and we can use these to populate the MP Checker tool. So MP Checker is a tool from Minor Planet Center that you can use to help determine whether or not this may be an already known object. So here's the first observation, the second, and the third. So as you can see, that's another great thing about Tycho, is that even though there was a star right here, we are still able to get good measurements. And that's because, of course, it uses a different layer here to generate these observations. So it's able to take out that stationary object for us. Okay, so how do we do that? Well, we want to, again, determine if this is really a new object. So first we get the observation, so we say view. We don't have any other existing observations at this point, so we just go to view, and this gives us the observations formatted in MPC 1992 format. So let's go ahead and take a look at that. Okay, so the MP checker tool, again, this is from the Minor Planet Center, so minorplanetcenter.net is the address. And what you want to do is go down to Other Observer Services and then choose MP Checker. So when you go here, you can then populate this window with the observations, and you want to choose this radio button that says you want to evaluate around these observations. So when you do that, you click Produce List, and it's then going to populate some results to indicate whether or not those observations match with an already known object. So we give it a moment to run the computation, and hopefully here in a moment we'll have some results to look at. Okay, so it came back with one object here, this 2019 OV2, and as you can see, this is a match because the offsets here are 0 and 0. So when they're that close to 0, and effectively they are 0, then you can be pretty much 100% certain that this is in fact the object, 2019 OV2. Another way you can determine that is, okay, let's assume that it is 2019 OV2, so we're going to edit the designation. So we're going to right click and choose Edit Designation, and we're going to say it's 2019 OV2. And when we do that, we can now choose View with Existing Observations. So this allows us to compare our observations of this object with others. And so, again, mine were taken on September 1st. You can see there are some more recent ones since that time frame. But we'll go ahead and view and the Find Orb program. So Find Orb is a wonderful program for this. It allows you to evaluate the measurements, and hopefully we can see what's going on here. Oh, okay, the reason for that error is that I had actually already submitted these particular measurements on September 1st. So I'm just going to delete those and substitute with these, again, just for this example. So View and Find Orb, and as you can see, the September 1st, yeah, so we had good measurements of the object. So Q62 is the station code here, and indeed this is how you can confirm that this is in fact the object. So we had 0.62 was our worst residual. So yeah, you can look at this and see, you know, the object, the magnitude computed is 18 and a half, just about. So it's expected to be magnitude 18 and a half. And so that's pretty good, because again, this is a 127 millimeter refractor, and we didn't even know this object was in that field of view. We just said, okay, let's take this set of images and stack them in hundreds, thousands of different possible combinations, and lo and behold, it came back with this object is track number 28. So, and this is in fact a near-Earth asteroid. So, you know, if we had gotten to this field earlier, then we would have actually discovered a near-Earth object with a 127 millimeter refractor. So I think that's pretty cool. So again, kind of the whole purpose of this video is to demonstrate how you can discover new asteroids. So unfortunately, track number 28 did not pan out for us because it matched up with a known asteroid. And as you can see, it's actually fairly bright. So we didn't even need to have a full 3 hours of imaging time to detect it in the first place. However, it is a good first step As you can see here, the tracks are sorted by quality, and what that means is that the first track, for example, is very bright in comparison to the one that we were just looking at. So as you go through this list of tracks, they get fainter and fainter. The detections get fainter and fainter. So what we want to do is proceed forward, and we skip the ones that, again, they're matched up with a known object. And so track number 80 here, this one looks to be a true detection. And so we can right click and verify the track, and again that gives us an animation that we can look at, and if we wanted to we could add observations of it, and then that gives us a way to build up our list of measurements. And I could do the same thing as before with OV2 and determine whether or not that matches up with a known asteroid using the NP checker tool. Of course this takes a bit of time because this tool is not particularly fast, so I won't do this for every object, but I will just show you kind of what we can expect to see as we work through this process. So hopefully here in a moment we'll get some results, and as you see the offsets here are such that this is actually possibly a discovery because they're simply too far off to match with the observations that we generated here. So this track number 80 is a potential discovery, but it's also probably just a boring main belt asteroid. I say boring because you know that's where most asteroids are simply main belt asteroids. So, but in that context, it's still, even so, it is still somewhat exciting that maybe this could be a new discovery. Track number 82, same thing. This looks to be a true detection. Track number 88, same thing. And so, but I do want to show you an example of a false detection. So track number 111 here is, as you can see, you might say, oh, maybe that's a fast-moving object that has a bit of a streak to it. But the truth is, upon further inspection, again, you can right-click, verify track, you get the animation, and it looks like only on 2 of the 3 stacks you have this sort of artifact. And the way you can verify it even further is you can look at each exposure individually. So as you go through these exposures, you'll note that the artifact shows up later on. And so this is definitely a false detection, so you would certainly not want to generate measurements on this. Okay, so to move the video along a bit further, I want to go ahead and skip to a more interesting object here. So this is track number 149. So the speed of the object here is not too terribly interesting, but what is interesting is its position angle. So most main belt asteroids have a position angle between 2 and 300 degrees, whereas this object has a position angle of 137 degrees. So we do note that it is a true detection, at least it appears to be here. So when we verify track, we can further validate that. So as you can see in the animation, it does look like a true detection. So we're going to go ahead and add observations of this object, and then go ahead and say, well, okay, is this potentially a discovery? So we can go ahead and copy into the NP checker tool, and then determine again whether or not it matches up with a known object. So we'll give it a moment here to run the computation and see what comes back. Alright, so it came back with the 2019 MW3 is a match. The offsets are 0 and 0. And on the other hand, this is actually a near-Earth object. So even though we did not discover this object, it's still pretty exciting because this is now the second near-Earth object that we've detected in the same field of view of our 127mm refractor. So I think that's pretty cool. But now that we know what this object is, again, we can edit the designation. So we can put in 2019 MW3, and this allows us to compare with other observations of the object and get a little bit more information about it. So again, this is September 1st is when I acquired these images. So as you see here, these are the observations that we just generated. It does look like I have a 1.5 here, but that's on the last measurement, which again, that one had some star interference. Find orb says the computed magnitude is 20. As you see, 5 days later, G96 also got the object, they said mag 20 as well. So really, again, I think that's pretty cool. This is a very small aperture-wise instrument, yet it's able to detect a magnitude 20 near-Earth object. So even though we didn't discover it, we still were able to detect it. So I think that's pretty cool. Now to move things along a bit further, I'm going to go ahead and skip to track number 208 here. So this one has a little bit higher speed, but it's probably still just a main belt asteroid. But the reason I'm honing in on this object is because one, it is a bit faint. So I originally was not sure that this would be a true detection because it doesn't really stand out from the background all that well. But upon further inspection, as you see here with the animation, let me not do that just yet. With the animation, you can see that it does seem to be a legitimate detection. So we go ahead and add observations of it, and again we can run the MP checker tool just one more time here and verify whether or not this is in fact a new object. So let's just go ahead and do that real quick, and again give the tool a moment here to run through. Alright, so it came back with two results, and neither of them match up with the object. The offsets are too high, so this is in fact a candidate for discovery. So that's exciting. And actually, throughout this whole list of tracks here, these are the ones that were candidates for discovery, with the exception of track 1 and track 28 and 149. So 17, as you can see, a total of 17 when you take into account the others here, candidates for discovery. So that's pretty cool. In other words, in 3 hours of imaging time, we were able to have 17 candidates for discovery. So I'm going to spend a bit more time now on this object. So this is an example. The whole purpose of this video is a demonstration. So how would you go about discovering an object? So part of the discovery process is you get your first night of observations, and then you follow up to establish a better orbit of that object. So again, this is our first night. This was September 1st, and then I was able to follow it up on September 2nd, the next night thereafter. So let's go ahead and take a look and see what that looks like. Okay, so this is going to be the second night of observations. In other words, we're going to perform follow-up of that object that we looked at earlier. So here are the images, and because I'm following up the object, I can go ahead and use a larger instrument, which has a couple of advantages. The first of which, of course, is that in this case it's a 500mm reflector, so we shouldn't need to have 3 hours of imaging time to detect the object. And secondly, the larger instrument also offers better precision measurements, so we can get more precise astrometry, and that helps to establish a better orbit of the object. So what we want to do, at least what I like to do to start with, is I go to Tools, Existing Observations, and I go ahead and paste in the observations I had from the first night. And then I choose Attach Ephemeris to Dataset. So this is a modified version of Find Orb, which allows me to determine for each image whether or not the object is in the field of view. So it's not really required that you do this, but it's a convenient feature in my opinion. So the next thing we want to do is run the tracker. So this will allow us to see if the object is present, and if so, whether or not we can then get some observations on it. So I talk about how to do this in other materials, so I won't go into the details. But this is a known object, so we'll use the dataset ephemeris. So it limits the speed and position angle, and that helps to limit the number of motion vectors, which in turn means that it runs faster. So it's always nice whenever you can reduce the amount of processing time. So we'll give the tracker a moment to process the data and hopefully have some results. Okay, it says no tracks identified, so that's the message that's always discouraging. But we won't give up just yet, so we'll go ahead and run the tracker again, and this time we'll simply use a more sensitive detection threshold. So on this part here, I'll lower it down to say 1, and then run it again. So basically what I'm doing is I'm saying, okay, you know, go ahead and take more time, analyze the data, and run at a more sensitive threshold. So it's taken a bit longer to process the data, but again, the main goal is to recover the object. So that's okay if it takes a few more minutes, then that's acceptable. Okay, so it looks like the first track here is a possibility. So what's surprising to me is that even in this larger instrument, the 500 millimeter reflector, it had difficulty detecting this object. In other words, you know, 3 hours of imaging time with a 127 millimeter refractor, it was able to detect it. And this, on the other hand, is about almost an hour and a half of imaging time. The exposures here are 60 seconds, so the refractor had 3-minute long exposures. In this case, the reflector has 1-minute long exposures, and the total imaging time is 77 minutes here. So anyhow, I'm still surprised by that because 500 millimeters, that's 20 inches compared to 127, in other words, 5 inch. So by the area, the reflector should have been should be 15 times more light gathering power. But anyway, this is not exactly apples to apples because of course it is a different night. Maybe seeing conditions weren't so good. So I'm not going to go into all that in this video. Again, the goal is to say yes, we were able to follow it up. So we go ahead and load up the star catalog and verify that this is in fact the object. So you can see it here in the animation. This looks to be like the detection for sure. So we'll add observations, and we'll go ahead and use, you would want to use the same track ID. So I don't recall off the top of my head what that was. But what we can do is, I had pasted it here in observation. So it was 1676, and that's from a previous report. So anyway, edit designation 1676. So anyhow, what you can do then is open up another instance of Notepad or whatever tool you like to use, and you can say, okay, before I copy those, these are the September 1st observations, and these are the September 2nd observations. All right. So you now have 2 nights of observations on the object. So again, I can use find orb and determine whether or not there's a link. So there you have it. Find orb agrees that these observations on the second night are those of the same object as that in the first night. So, and you can see the improvement here. So the refractor has 2.73 arc seconds per pixel as its plate scale, so it doesn't really achieve a very good measurement, the precision that you do with the other instrument here, which has, I believe, a plate scale of 0.82 arc seconds per pixel. So naturally, you're going to achieve better precision with this instrument, certainly at this plate scale. And so anyway, that's kind of the demonstration here, is we were able to, first and foremost, discover the object. And so in that scenario, we're not overly concerned with having really precise measurements when we're just discovering the object. And then when we follow up the object, then we can use a larger instrument and get better measurements of it. So you've now seen how to detect the object, and you've been able to confirm through the MP checker tool that it is a candidate for discovery, and now you have seen how to follow up observations on that object. So again, if you wanted to, you could take this set of 2 night observations, run it through NP checker, and you get the same result. It will not match up with a known object. Now the other thing you could do is run it through NEO rating tool, and so you choose all orbit classes, and it will help determine maybe if it is a NEO or something to that effect. So we did not really anticipate it to be a NEO, but it may be something interesting nonetheless, at least somewhat interesting. Anyway, this gives you some other possibilities of what the object might be. So having done that, the next step, as you see here, still does not match up with a known object. The next step would be simply to achieve a longer arc as far as the measurements are concerned. So you now have 2 night observations, so now you want to extend that. So you wait a week or so and follow it up. In my case, with this object, timing conditions weren't that great, so I actually waited several weeks to follow it up. So just to conclude the video, let me go ahead and show you what that looks like. Okay, so this is the 3rd and final night of observations for this object. So I am using another instrument. It is also 500 millimeters, just like the previous one. However, the field of view is larger. And so that comes in handy because I have waited several weeks to reacquire the object, and consequently the uncertainty of the orbit has grown quite a bit, which means that we don't know exactly where the object is, and we also don't, for that matter, know exactly what its motion should be. So it's kind of a risk to wait this long, but we'll see what happens. These are 60 images, they're 3 minutes each, and so this is 3 hours of total imaging time, just like it was on the first night with the refractor telescope. So given that the imaging time is the same, but we have a much larger instrument, we really hope to be able to detect the object. So I'm going to start off, again, Tools, Existing Observations, and I'm going to paste in the observations that I have up to this point. So attach ephemeris to dataset, and this in turn is going to give me a starting point. Again, because of the uncertainty of the orbit at this point, we cannot trust this ephemeris information too much, but it will give us a path going forward. So I'm going to go ahead and run the tracker, and hopefully we'll be able to recover the object. So again, we can go ahead and say that this is a known object, and to go ahead and use dataset ephemeris. So again, I say it's a starting point. If we don't find the object, then we can certainly widen the search parameters. We could increase or improve the detection sensitivity. So we have some options if we don't find it initially, but we're going to go ahead and just see what happens on the first try. So I'm going to go ahead and let the tracker run with those settings, and hopefully, especially since we have 3 hours of imaging data, hopefully it will be able to detect it. So I'll go ahead and give it a moment here, and we'll see what kind of results we get. Okay, so here are the results, and as before, if we wanted to, we could load MPC orbital database to compare with known objects, but since we confine the search space to that of the object that we're recovering, we don't expect there to be any actual matches other than this first track is a true detection, and it looks like there's promise there that that is the object that we are trying to recover. So let's go ahead and load up the star catalog and create measurements of this object. So as I zoom in, you can see that this is in fact a true detection. So I'm going to go ahead and generate 3 observations on that. And we want to go ahead and try to use the same track ID that we've used before. And at this point, what we can do is then view these observations and then insert the other 2 nights of observations. So what we're trying to do here is establish whether or not this is the same object that we had originally. So find orb, it tells us that yes, it is in fact the same object. And in other words, these observations, the residuals are very good, such that we can be confident that this is the same object. These are observations belonging to the same object as in September 1st and 2nd. So that's very good. We have 9 observations total, spanning 26 days. So we've essentially been able to discover and follow up the object. Now, I wanted to also point out the uncertainty aspect of the orbit. As you see here, even though we have almost a 1 square degree field of view with this instrument, so I had set up the imaging plan, so that according to the ephemeris generated by Find Orb, the object should have been here if the uncertainty were 0. So in other words, but as you see, having waited several weeks from those first 2 nights of observations, the uncertainty was such that here the object is instead. And so having this larger field of view is certainly helpful. And the other aspect too is it's not just the location of the object, but it's also the motion of the object that becomes uncertain over time. So for example, Find Orb said that the speed of the object should be 0.61 and position angle 204. And again, that's based upon just those first 2 nights. But as you see here, the tracker actually thinks that the speed should be 0.68 and position angle 205. So you might wonder, how much of a difference is that really? So we can actually look at that. So if I go ahead and create, for example, 1 observation of the object, this will create a stack of all the images. So here's the object with all the images stacked together according to the 1 motion specified here. So obviously this looks like a true detection. So the question is, what would have happened if we had used the ephemeris information from just those first 2 nights? In other words, if we had used them directly. So if we had done 0.61 and 204, what does that look like? So I can create that stack, and as you can see, the object is now streaked out. So having 0.61 is quite different than 0.68. So in other words, if we had used simply just 1 motion vector and said, yeah, let's go ahead and use 0.61 and 204, we would not have found the object. Or if we'd had, certainly we would not have found it in location, and we would have been a bit puzzled as to whether or not this might have been the object. But the tracker, that's the whole purpose of it, is that it can explore all these different motion vectors, and it was able to identify 0.68 as the actual speed of the object, and that's where you get a nice presentation right there. So Tycho does offer other more automated ways to perform this discovery and follow-up, and so I may do another video on that as well. But for now, I will also do a part 2, which will go into some detail on tips and tricks and ideas on exposure time, total imaging time, plate scale, and that sort of thing. So, but for now, hopefully this has given you some insight on how you can discover new asteroids. So thanks for watching, and see you next time.